Good afternoon, everyone, and welcome to this European Nuclear Society webinar on powering advanced reactor projects, the role of fuel innovation. My name is Diego Jaramillo Sierra. I'm a nuclear fuel analyst at the Joint Research Center of the European Commission. And today I have the pleasure of moderating this session on behalf of the European Nuclear Society and Jóvenes Nucleares. This webinar is organized together with Framatome and ENS Corporate Member. We will look on how fuel innovation can support advanced reactor technologies, including SMRs and Advanced Modular Reactors. Discussions will address how existing fuel experience can support emerging reactor concepts, the role of innovation in fuel development and qualification, and the technical and industrial challenges associated with scaling up the future developments. Again, as a practical reminder, before we begin, the audience will interact through the chat only. So please write your questions during the presentation. We will collect them and address them in the Q&A during the final part of the webinar. Today, we have the pleasure to have two speakers from Framatome. Alice Dufresne is Domain Manager from SMR, Core Components and Additive Manufacturing within Framatome Fuel Business Unit. Her work covers SMRs and fuel assembly deployment, from early concepts to industrial implementation. She also brings previous experience from OECD Nuclear Energy Agency. She has coordinated international activities on nuclear fuel and materials, and she also holds a PhD in material science from Aix-Marseille University and completed a postdoctoral experience at MIT. Oliver Tuga is Innovation and Advanced Fuel Domain Manager within Framatome Fuel Business Unit. He has more than 30 years of experience in material science with a strong focus on iridium-based ceramic and metallic fuel systems. Before joining Framatome, he was full professor at the University of Lille, where he led academic and industrial research activities related to the nuclear fuel cycle. Oliver, Alice, thank you very much for joining us today. The floor is yours.
So thank you, Diego. Hello, everyone. So I'm going to start. So in response to the growing needs related to fuel for low and medium power reactors, Framatome is structured through its innovative reactor fuel hub to address the challenges of the fuel availability for the modular reactors. And for that, Framatome has selected 4 technologies, which are for advanced modular reactors, which are considered as generation 4 systems. So for that, Framatome has selected the high temperature gas-cooled reactors, which are using trisofuel, and also fast breeder reactors, which are using either metallic fuel or ceramic fuel, such as MOX fuels. So MOX fuel is a mixture of uranium oxide and plutonium oxide. And regarding the second type of modular reactors, they are more likely based on third generation systems. They are light water, small modular reactors. And for that, Framatome is developing fuel solutions for both pressurized water reactors and boiling water reactors. Regarding the fuel for light water, small modular reactors, they will be presented in more detail in the second part of this presentation by my colleague, Alice. So with over 65 years of experience, Framatome can develop cutting-edge fuel solutions for the needs of our customers and partners, also including startups. Next slide, please. So the innovative reactor fuel hubs leverage Framatome broad organization, allowing to mobilize the best competencies and technology to fulfill both SMR and AMR project needs to develop and deliver unique and comprehensive fuel solution for fabrication, qualification, and licensing. So Framatome Innovative Reactor Fuel Hub, as you can see in this map, is a multi-regional, ultra-connected network that brings together both our production and manufacturing capabilities with our fuel design unit. So let's start here by prototyping capabilities for light water SMR reactors design, which are primarily located in Karlstein in Germany, where full-scale fuel assembly can be manufactured and tested. Now, if we move to fuel for advanced modular reactors, let's start by the west coast of United States in Richland, where Framatome has its excellent center for advanced fuel. So Richland site provide various fuel types and services, including deconversion of HAEDU+, in the near future deconversion of HAEDU, all in order to convert UO2 powder to uranium metals and trisofuel. Now, if we come back to Europe and in France, here in the middle of the map, so Framatome Roman, through CERCA, is producing a fuel set of high-enriched uranium metallic fuel, such as UMO, uranium zirconium, or USI fuel, which can be used for specific fuel demands, such as for MMR project, including space application. In addition to the fast prototyping lab that I just talked about, Framatome is currently installing a TRISO pilot line on the same site. It should be also mentioned that within the fast prototyping lab in Romans, additive manufacturing is currently developed, allowing to print fuel components based on zirconium powder, but also to print uranium-based fuel. Regarding the supply chain for the zirconium supply chain, Framatome has a fully integrated supply chain for the fuel component manufacturing for zirconium-based alloys, which comprise several industrial sites, among which Framatome Paimboeuf, here in the west of France, where we have a tubing line, but also where the PVD coating of the tubes are performed. Regarding stainless steel tubing, Framatome is relying on Montbard site here in the northeast of France, where we have, when we stretch stainless steel tubes. So all this production facility for components can rely on our component research center here in Eugene, in south of France, where can be performed a fabrication simulation, but also which can provide expertise on metallurgy for both zirconium-based alloys and stainless steel. In addition, as I said, Framatome is relying also on its design fuel units, which are located in Germany, in Erlangen, in France, in Lyon, and in the United States, on both on our site, either in Lynchburg and in Richland. Next slide, please. Regarding fuel solution for fast breeder reactor, Framatome has a long experience on fuel component fabrication, which is based on our involvement in the past French programs such as Phoenix and Super Phoenix. As an example, Framatome has delivered more than 300,000 fuel pins, as well as more than 1,300 hexagonal tubes for these two French programs. So in addition, it should be mentioned that Framatome is also the current MOX designer for the PWR fleet. And in United States, Framatome is working on the metallization process of HAEDU fuel in cooperation with TerraPower through the development of a pilot line at our nuclear site in Richland, in the west-north coast of the United States. So this metallization pilot line, which is operational since 2025, works on the qualifications of the conversion of uranium oxide into metallic HAEDU. So the recent technical success of the uranium metal production support a long-term objective of building a robust domestic HAEDU supply chain in the United States and to help to provide fuel for the North American market. Next slide, please. So regarding now the fuel for HTGR and MMR project, so regarding the shift in the timeline project between United States and Europe, Framatome selected two approaches to ensure a full coverage of the HTGR project regarding the TRISO availability and innovation. So in United States, Framatome Richland combined the deconversion program for high-assay low-enriched uranium, as well as uranium production, to the TRISO fuel manufacturing. For this last stage, Framatome has established a joint venture with Standard Nuclear, formerly known as USNC, to produce at industrial scale TRISO fuel. And I will give more detail about the objective and the mission of the joint venture in the coming slide. In parallel, in Europe, Framatome is establishing a new sovereign capability in France, in Romans, for the European HTGR reactor project by installing a TRISO pilot line in Romans. So the objective of this TRISO pilot line is mainly for qualification and licensing, but also to provide innovation of TRISO, as well as to improve the manufacturing process. And I will give more detail about the TRISO pilot line very soon. So please, can you change the slide? So regarding Framatome's strategy in North America, as I said, it is mainly for production of the TRISO fuel. And for that, we have signed a joint venture with Standard Nuclear in September 2025. It is a full cooperation comprising functional technology and production line provided by Standard Nuclear, fully adapted in an industrial nuclear environment from Framatome, providing the infrastructure, staffing, and licensing. So the joint venture will produce typically UCO TRISO particles within SiC compact, but on the demand, the production can be adapted to UO2 TRISO particles, also in graphite matrix, in order to have also different geometries of fuel element, such as compact or pebble. So the production will start very soon in 2027, and the capacity will increase depending on the demand of the market. Next slide, please. Regarding now Framatome's strategy in Europe, so Framatome is installing a TRISO pilot line in Romans, in France, very close to our first fast prototyping lab, the CRIL facility that maybe some of you already know. The TRISO pilot line comprises here the fabrication of the kernel, it is in green. All the heat treatment for coating, for conversion, sintering, and for coating, as well as here in pink, the capability for compacting, as well as the quality control, along with all the utilities and facilities needed for storage and other shipping and conditioning of samples. The project has been started early 2025, and it is planned to be operational at the end of 2027. Next slide, please. So the objective of the pilot line, as I said, is optimization and qualification of the manufacturing process for typically UO2 and UCO type of triso particles. In case of qualification requiring irradiation test, Framatome will be able to handle and to manufacture samples with enrichment up to 20%. The second objective of the TRISO pilot line is also to develop innovation and with a focus on the optimization of the manufacturing process in order to reduce the manufacturing cost of the TRISO particles, which is a challenge. So in short, please note that the pilot line is fully open to partners either from Europe, Japan, and United States for joint program. It will have the capability to manufacture both UCO and UO2 type of particles within a graphite matrix. And prototype sample can be obtained for further qualification under irradiation if needed. And regarding innovation, we will work on optimizing the manufacturing process for reducing the fabrication cost, but also we will work on the reprocessing of the liquid effluent, which is a key point in the management of the production of TRISO fuel. Next slide, please. Along with the prototyping facility, Framatome is also developing methods for fuel safety justification based on code and method. And for that, we are already relying on thermomechanical and diffusion code that has been developed in cooperation with CEA, the Atlas code, which is able to modelize the fuel behavior at the particle scale. Now, Framatome is developing its own industrial codes at a larger scale, at the fuel element scale, in order to be able to interface with the core physics by including this new computational code into our fully integrated neutronics and thermohydraulics packages for fuel modelization. And here, I'm stopping the presentation of the development of the fuel for AMRs, and I let the floor to my colleagues. Alice, thank you for your attention.
Okay, so now I will go to, let's say, more known fuel products that are proposed by Framatome for what we call light water small modular reactors or small modular reactors in general for short. So we know these SMRs require tailored fuel solution because there is a diversity of design in the new concepts under development, and they also have needs for fast solution to support their deployment timelines. So at Framatome, we leverage the decades of expertise and experience we have and build on our qualified fuel products for PWR and BWR to accelerate fuel development for SMRs, thanks to the use of proven technologies that is relying on a well-established and ready supply chain. This portfolio of solutions rely on existing standard technobricks that are combined in a modular way to maximize the performance of the SMR from a fuel standpoint, both from an economic performance standpoint and a technical performance standpoint. And for this, we are engaged in developing value-adding features and also making sure that this offer matches the need of SMR developers. Okay, next slide, please. Okay, I think the video doesn't work. So yeah, we'll put the link for the video after the webinar. So how do we adapt the existing fuel product to SMR design? So we have our portfolio of existing proven fuel products, best in class, that enable the fast track design adaptation, manufacturing, licensing, and deployment to markets. For non-boiling light water SMR, the Gaia fuel product is the starting point. And this is possible thanks to the use by SMR developers of the standard 17 by 17 array for this type of reactor. For boiling SMRs, Atrium 11 fuel, which has a very good operational experience feedback with 0 leaker so far after 10 years in the US, is the starting point for this type of reactor. We know that in the SMR designs under development, there are some deviation from the standard in terms of core cavity height. So there is a proposed adaptation of the fuel and core components to the various heights, including their shipment solution. And the Framatome has capabilities for analytical modeling and also full-scale or component scale testing to support the qualification of the SMR tailored product. So we really have the ability to propose a fit-to-need architecture and a design that is based on proven products and technologies. Next slide, please. How we can improve the economics and the fuel cycle of SMRs. We rely on our expertise of a fuel designer to propose high-resolution neutronic design to optimize the fuel utilization and improve the reactor economics. And this is possible thanks to play on the enrichment and the burnable absorber zoning. In addition to that, we can leverage the Advanced Fuel Management Program that is on the way to deliver LEU plus fuel with enrichment higher than 5%. It's actually happening in our facility, fuel fabrication facility in Richland in the US on the West Coast that was presented by Olivier on the map. So this program includes the fuel, the design, the licensing, the fuel fabrication, and the shipment, and going above the 5% limit allow, of course, for the installed base to go to longer cycle, 24-month cycle, but for SMR is also a way, an additional lever to improve the fuel cycle economics thanks to this added flexibility. In terms of digital tools, we also have an optimization system called Fargo that optimizes the fuel assembly design and the fuel loading pattern, that it is adapted to various core size. So from the smallest SMRs with between 30 and 40 fuel assemblies per core to an EPR. It is key to really improve fuel loading patterns and so improve the fuel cycle economics while being very compliant with all the safety margins requirements. So, and it is a tool that allows improving the core design for flexible operation with increased requirements in terms of load following and power operate. So all these tools are available and applicable to SMR development to support the SMR economics from a fuel cycle standpoint. Next, please. Framatome has also developed an enhanced accident tolerant fuel program called Protect, and it is compatible with SMR. So the Protect program is the leading EATF solution that is supporting reactor safety and economics. It started the first irradiation of this chrome-coated fuel rod started in 2016 in Gösgen in Switzerland. We had the first irradiation of a fully coated fuel assembly started in 2021, and the industrial deployment of the capability is on the way to have first reload capacity next year. This program, EATF program, has been demonstrated for performance up to burn-up of 73 gigawatt-day per ton, and it has a demonstrated compatibility with pH control systems based on KOH or LEOH. So it's compatible with the SMRs. Okay, next slide, please. Okay, we know also that with the variety of SMR designs, we have some new specific conditions proposed or embarked in some of these concepts. We have, for example, the case of natural circulation, for which the core contribution to the primary loop pressure loss is typically of 40%. So anything that can be improved in terms of pressure loss on the fuel assembly is an improvement in terms of what can be obtained as heat exchange efficiency and so the overall plant efficiency and safety. So what is ongoing is to optimize the nozzles, top and bottom nozzles, to really reduce their pressure loss. And just to give you an order of magnitude of what it is to be in natural circulation condition, it's typically in a fuel assembly, the mass flow rate is divided by 20 in comparison with the typical PWR. So there is simplification that can be done on the fuel assembly to optimize it with respect to pressure loss. There is an illustration here on how much we can adjust the top nozzle to reduce the spring force on the fuel assembly. But clearly, what I want to convey as message here is that with variation in the core design, there is modularity that can improve the value of the fuel assembly to really meet specific needs and unlock new possibilities in terms of performance. Next, please. Okay, and to close this presentation, I also want to highlight how much the fact that we start from a standard proven techno-brick approach can accelerate the development of fuel, because this use of existing components and adaptation of the existing components allow to really rely on the global supply chain and the manufacturing facilities that are already qualified, established for the current fuel assemblies, fuel products for the installed base. So we are the proposed approach is to rely on standard materials and components, to have an approach that adjustment that is really targeting compatibility and value-adding feature to really use as much as possible the proven manufacturing technologies and processes, and of course rely on the robust qualification process that is already supporting our fuel delivery on a daily basis. In addition, the in-house analytical modeling, simulation, and testing capabilities ensure the compliance of the proposed product with the regulatory requirements and the performance requirements. And last, there is also an available fuel services portfolio for SMRs. So really, the strategy is to rely on proven technologies and infrastructure to allow fast market implementation from the design to the licensing to the manufacturing and the shipment. Next, please. Okay, this is the concluding slide. So from the concept to manufacturing, Framatome is ready to support the fuel journey of SMRs and AMRs. So thank you for your time, and we're happy to take the questions in the chat.
Thank you very much, Elise. And Oliver, thank you for the clear presentation. It was really exciting to see all the innovation in the fuel sector. We will now move to the Q&A session. We have already a few questions about TRISO so I'm going to group them. And would be, has Framatome conduct testing or qualification work on thorium-based TRISO fuel? And do you have planned to conduct irradiation testing for TRISO fuels that will be manufactured at the Romans and Richland facilities?
So regarding irradiation, so either at Roman or Richland site, Framatome is positioned as a fuel vendor or is in preparation of the industrialization to be a fuel vendor. So the first step means that we are supporting partners, typically HTGR developers. So the first irradiation will be led by our partner. In a second time, and maybe in Roman, when Framatome will develop its own fuel or improve fuel, yes, for sure, we are planning to perform irradiation experiment.
Thank you very much. Now, continue always with the TRISO fuel. There is a question that is about TRISO fuel is considered safer because it has lower gaseous fission product release during severe accidents. In your view, could regulators modify the LOCA criteria for zirconium chromium coated cladding when it is combined with TRISO fuel pellets?
That's not a question for Framatome. That's a question for the safety authority. But it's typically, that's a good question. That it is, so there is many several publications about this concept of introducing TRISO fuel into a typical fuel rods, zirconium fuel rods. And for example, the FCM concept developed by ORNL and we developed by national US national labs was considered or is considered or is regarded as a potential solution to improve the safety of PWR when introduced in zirconium tubes. Yes, but I cannot answer, of course, this question about the safety and regulation.
Thank you. The next question is directed to Alice. It's, will you explain the fine enrichment and burnable absorber tuning a bit more? Is the tuning in axial or radial direction or something else?
Okay, so you can have the two. So in the sense that you can have axial zoning in a fuel assembly to compensate for some axial leakage, and also radial in the sense that within a fuel assemblies you can have various enrichment rods with different enrichment in a given fuel assemblies. So the goal is really to optimize, taking into account the design with smaller cores that we know are less favorable because of the increased leakage, and combine it with what can be optimized versus what is also sound in terms of manufacturability and find the optimal value proposition to reduce the fuel cycle cost.
Thank you very much. The next question is always to Alice. It's about, in your opinion, what are the main barriers to being able to start using LEU Plus with higher of 5% enrichment in light water reactor fuels?
So on this, there is, of course, the industrial capacities to go to higher enrichment and all the licensing that goes with it for a fuel fabrication plant. But I would say there are no more barriers in the sense that we have an industrial capacity that is licensed today. So it will be delivered shortly in the US for longer fuel cycles. So the question is more, how much does it brings values? And that's the reason why I emphasize the longer fuel cycles, going from 18 months to 24 months. It means that every 6 years you save one outage. So the benefit of the extra electricity production during this spared outage compensate the slight increased cost of fuel assembly with higher enrichment and allows to bring value to the utilities. And the same can be obtained for SMR. So it's a matter of how do you design your core, and but the capacity exists today to have reload quantities in the very near future.
Okay, thank you very much. And also regarding the economics, there is a question about what is the cost impact of Protect in comparison to standard uncoated fuel?
So for Protect?
Yes.
I'm sorry, it's out of my expertise, so I don't know in terms of, I cannot answer that question in terms of cost.
We understand. Now changing a little bit the fuel type, there is a question about what type of fuel salts are you exploring, if there is any?
Okay, so regarding molten salt reactors, they are using liquid salt, and it is not the field of expertise of Framatome. So Framatome hasn't selected fuel for molten salt reactors. We can provide, as Framatome, as reactor designer, some assistance for the design of the reactors, but nothing on the fuel, unfortunately. Thank you.
Now, the next question will be, what is the time horizon for Framatome's development work on fuel height addition of Gaia and nozzle pressure drop reduction in Atrium 1.1?
So for the fuel height, so we've already manufactured elements with the reduced size. So this is something we know how to do. And so the timeline is then more the licensing of a fuel within a given reactors, but there is manufacturability. Of course, it depends always below a certain height. It brings more challenges, but for the and challenges in the sense of manufacturing updates. So there is maybe more needs depending on the height, but really globally, it's an adaptation of the existing manufacturing lines with something that is compatible. The manufacturing lines are compatible with the vast majority of fuel adjustments. So I couldn't see the question in the chat. So the timelines. So the timelines is more a matter of licensing of the fuel that goes with the SMR timeline to license their concept rather than the manufacturing of it. And the nozzle pressure drop reduction in atrium, I cannot answer this question.
Thank you. Now, there is a question about consideration of switching to hexagonal grids.
So I don't know if it's for SMRs or fast breeders.
There are two questions regarding that also.
Yeah, for the SMR standpoint, I would say that what I presented here was relying on the square 17 by 17 array. That is the most conventional conventional pattern, fuel assembly pattern for PWR. For the hexagonal, we are designing VVR fuel with the hexagonal pattern. So we have now designs with hexagonal patterns. However, so far for SMRs, we've never been working on adjustments to an hexagonal patterns.
Okay. Now, there is a question about projects regarding the liquid metal fast breeder reactors, if you want to mention something about it.
So, Framatome, as a fuel designer, is considering fuel for fast breeder reactors in cooperation with developers. Typically in the United States, most of the developers rely on metallic fuel based on uranium zirconium, such as TerraPower, as you know, and we work with TerraPower in very close relation to manufacture their fuel. In Europe, and most of fast breeder developers rely on ceramic fuel. So either HALEU UO2 pellets or MOX fuel. And we also initiate collaboration with newcomers developing such fuel concept.
Okay. Now, the next question will be, will the future demand for SMRs be absorbed by current manufacturing sites? Or will there be dedicated sites for manufacturing SMR fuel in the future?
This is, I think, a very scenario-dependent answer. So how many new SMRs will be built, at what time frame, and in what transition with respect to the existing installed base? To say it in a different way, how much globally the fuel demand from, let's say, relatively conventional fuel products will increase by 2035, by 2040, by 2050. What is clear is that we have the capabilities today for the foreseeable increased demand, and also that with the time to have, when there will be clear signal of higher demands for fuel, the lead time of coming up with increasing fuel fabrication capacity will be shorter than the lead time to see the demand increase. So the capacity, the manufacturing site capacity is not a bottleneck to supply fuel for SMRs.
Thank you. One additional question is, as you mentioned during the presentation, there are different fuel types. Do you expect the market to converge towards a few dominant standardized fuel technologies, or will fuel suppliers need to support many parallel fuel families for the next decade?
It's a tricky question because
it's very generic, so it's hard to know. What I'm trying to find it in the chat to see how it was phrased.
Yes, it's a very tricky question because now we can see developers with their own fuel design, and they have also designed the core physics based on the selected fuel. So it means that up to now, at the early stage development of these new reactors, it's clear that all developers want to have their own fuel. But it's clear that in the futures, maybe due to economics and to supply chain, standardization of fuels will be needed. It is a very generic answer. And Alice, if you want to add something more particular for SMR.
I think the standard approach benefits from the fact that we can leverage of the shared components. So to support the timelines of SMR deployments, relying on standard existing products has a real benefit. However, if we see the installed base, there is a variety in the fuel assembly design. So we not only have 17 by 17s for PWR, but also other arrays. So we've been living with this diversity, and we have products being delivered for this diverse fuel assembly arrays. So there will be. We know there is always a diversity. The closer you get to standards, the faster it is to deploy it. But there is always a diversity.
Yeah. There is a question that is looking forward even more in the future, and is, what do the post-ATF clad and pellet look like?
Okay, take that as an innovation, or?
It's a tricky question. It is, I think, even looking more forward into the future of innovation.
Yeah, I think this is clearly not in the frame of the support to the SMR deployment, near-term deployment, because this is something that is not ready yet. So not something that will support the first of a kind deployment if we want to be fast and demonstrate the feasibility and economic model of the SMRs. It's more a longer term topic that is addressed outside of the scope of the SMR, because as of today, in terms of volume, the main market is outside of the SMR.
Okay, I will make a question if there are none more questions in the chat, and it's about young professional skills in this landscape for fuel innovation. What are the skills that are needed to address the challenges of fuel innovation?
Some background in physics. First, I know it's yes.
I think an appetite for a complex field, because even we are in a constrained environment, and innovation will come from being creative while taking into account the boundary conditions. So this is possible if you are eager for the search of technical details that can have an impact and that you can optimize. So really, there is room for innovation, and it has to come with a creativity that is based on a sound technical knowledge.
Thank you very much. And I think I can thank you now properly for the presentation and the discussion. Also, I want to thank all the audience because of the really interesting questions and the participation of this webinar, as well as European Nuclear Society and Framatome for organizing this session. So Before closing, I will also encourage the students and young professionals of the audience to get involved in the national nuclear societies and young generation networks. And I think we can conclude like this. Thank you all for attending and have a good afternoon. Thank you very much.
Thank you, everyone.
Thank you very much. Thank you for your attention.